Okay, the second derivative test isn't a test that I use all the time, but it is actually pretty cool, so it's worth definitely going over. We're going to find the relative extrema using the second derivative test for f of x equals negative 3x to the fifth plus 5x cubed. Now, rather than give you all the steps all at once, we're going to write the first step down and then we're going to do it, okay? Then we'll write the second step down and then we'll do that step. So our first step is to find the critical numbers. So you remember how to find critical numbers. We find those from the first derivative. A critical number is also any restricted values from the function and or the first derivative. So here we are. Find the relative extrema using the second derivative test. So we've got a polynomial function. So our domain goes from negative infinity to positive infinity. And our first derivative is going to be negative 15 x to the fourth plus 15x squared. I'm going to factor out negative 15x squared, which is going to leave me x squared minus 1. So I've got three critical numbers. I'm going to set that equal to 0, and I get x equals 0, positive 1, and negative 1. So on a number line, I'm going to place those critical numbers, negative infinity to positive infinity, and that number line represents your domain. So negative 1, 0, and 1. Okay, now we're ready for the second step. The second step says use the second derivative test, and I'll tell you what that is in just a sec. Use the second derivative test. The second derivative test says if, there's two ifs, three ifs, if the second derivative is greater than 0, then f of c is a relative min. I did not get that wrong. If the second derivative is positive, then f of c is a relative minimum. I'm going to highlight that because that's the first part of your test. I mean, that's one definition or one piece of the test. The next one says if, let's say, if the second derivative isn't greater than 0, let's say if the second derivative is less than 0. This is true, it's the second derivative that we're talking about. Then f of c, that's your output in your original function, is a relative max. Okay, and we'll use a different colored highlighter for that one. So if the second derivative is positive, you have a relative min. If the second derivative is negative, you have a relative max. And if, let's say it's not greater or less than, let's say it's equal to 0, then the test fails. You got it, fails. And you have to go back, you have to resort back to your first derivative. So you have to use the first derivative to determine. Now, this one right here that I'm going to highlight in blue, yeah, it makes me blue. It makes me sad because when this happens, you have to go back and you just use your first derivative anyway. And then you find yourself sometimes saying, why didn't I just do it that way? Why didn't I just, since I was going to be doing that anyway, why did I? Well, because it doesn't always happen that it's going to fail. Okay, so I'm going to show you. Okay, our second derivative of x is equal to, I'm going to go to the first derivative, and first derivative is negative 15 x to the fourth, here's our first derivative, plus 15x squared. So the second derivative is negative 60x cubed plus 30x. Now we're going to test these values. Negative 1, is that an input that's going to give me a relative max or min? I'm going to test 0. Is that an input that's going to give me a relative max or min? And then I'm going to test positive 1. Is that an input that's going to give me a relative max or min? So we've got f double prime of negative 1. Let's see what that is equal to. If it's greater than 0, then it's a relative min. If it's less than 0, relative max. Equals 0, it fails, and we have to go back to the first derivative and test the first derivative. So f double prime of negative 1 is equal to, we're going to put negative 1 in to the second derivative. I get positive 60 minus 30 is negative 30. Is that correct? Negative 60 times, nope, that's positive 60 minus 30 is positive 30. That's a positive 30. 60 minus 30 is 30. 60 minus 30 is 30. So 30 is greater than 0. Therefore, f of negative 1 is a relative minimum. Excellent. That one right there I'm going to highlight in yellow because that happens to be greater than 0. It matches. I'm going to highlight there. F of negative 1 is a relative min. I'm having fun. I don't know about you, but I'm having tons of fun. Okay, let's try f double prime of 0. So we put a 0 in, and when I put a 0 in for x, I get a 0. That means that it fails the test. And that's a big fat ugh, right? Ugh. That's okay though. No worries, we're gonna there we go. Okay, and then our last one, let's try f double prime of positive 1. You put a positive 1 in, you're going to get negative 30, and that is less than 0. Therefore, f of 1 is a relative max. Now I've run out of room here. I've run out of room, so I'm going to have to take my work here and I'm going to have to shrink it. I'll resize it. There we go. And I'm going to do the same thing here. I'm going to shrink this. Don't you wish you could do this? You could do this if you get an iPad or if you get some kind of a tablet. You should ask for one for Christmas. Maybe Santa will bring you one. But I've heard that the PS5s are coming out and the Xboxes and all that, and I don't know how good those are anyway, because don't you have to buy new games? So I don't know. Maybe they changed it. Okay, back to math. Let's see. So what does this mean? So this means that I have to use, yeah, that ugh. I have to use the first derivative test. So now I have to go back to my first derivative here, and let's see what's happening. So my first derivative test, I'd like to make myself that note. So I need to see what's happening before 0 and what's happening after 0. Negative 1, that's going to be a relative max. No, relative min. Sorry, I was looking. It's a relative min. So for it to be a relative min, that means that we were decreasing and then increasing, right? And 1 is the input for your relative max. that means that you were decreasing, right? Decreasing, nope, increasing, and then decreasing. That's how you get a maximum. You're increasing and then decreasing. That's how you get a max. So if I'm increasing from -1 to 1, that means that 0, there's no extrema there at 0. So my extrema, I think it said relative extrema. My relative extrema, I'm going to have a relative min at f of -1, which is equal to, when I put f of -1 in, I'm going to get -3 times -1. I'm back up here now. -3 times -1 is 3. 3 minus 5 is -2. So I have a relative min at -2, and I have a relative max, not at, but of. It could be at on the y-axis, you know, but a relative min of -2 and a relative max of, when I put a 1 in, I'm going to get -3 plus 5, which is +2. And that's our answer. Yay. So there's our steps. That's how we go through and find our second derivative, or our relative extrema, using our second derivative test. Let's see if you can do this. So you go ahead and give this one a try. Okay, when you come back, press play when you're ready to come back, and then I'm going to have all the work there for you. Well, I'm going to go through the work. So here I go. Okay, we've got f prime of x. When I found f prime of x, I was able to get, let's see, I'm going to write down this step so that you can see if you did that part right. And then I further factored 2x squared times 2x minus 3, set it equal to 0, and I got critical numbers of 0 and 3/2. And then I found this, let's see, we're using our second derivative test. Then I found the second derivative. So the second derivative is equal to 12x squared minus 12x. And I set that equal to 0. No, I didn't set it equal to 0. I just factored it. This way I can use my second derivative test. So now I'm going to put 0 in, and I'm going to find f double prime of 0 and f double prime of 3/2, and I'm going to see if I have a relative max or a relative min. So I put a 0 in, and I get 0 times anything is 0, so this fails, right? Fails. And then when I put a 3/2 in, I get 3/2. That's a positive. A positive times a positive is a positive. So I'm just going to put positive right here, right? Which is greater than 0, so that's a relative min. So 3/2, I've got a relative min. So for it to be a relative min, I would have had to have been decreasing and then increasing. So decreasing and then increasing. So what's happening in this interval right here from -infinity to 0? So I'm going to go to that first derivative, go back to the first derivative, and I'm going to plug in a value between -infinity to 0 and see if we're increasing or decreasing. When I put in maybe a -10, I put a -10 in, and I'm going to get a positive times a negative, which is a negative. That's decreasing. So decreasing to decreasing, I don't have a relative max or min because my increasing isn't happening. I'm not going from decreasing to increasing. So therefore, the only relative extrema I have is at x equals 3/2, which is equal to f of 3/2, right? So I'm going to put a 3/2 in, and I'm going to get a value out. I'm going to come back to that in a minute. Now what I'd like you to do is I'd like you to tell me about the concavity. So press pause again, and let's talk about the concavity and the points of inflection. Okay, so if you have not yet done that, let's talk about the concavity and the points of inflection. Okay, welcome back. Meanwhile, I'm going to write the relative minimum is equal to f of 3/2, which is equal to, I'm getting negative 11 over 16. So hopefully you got that too. So that's our relative extrema that exists. Now we're going to talk about, concavity. So concavity, I have to go back to that second derivative, and I have to solve that second derivative equals 0. So I'm going to get 0 and 1. 0 and 1. So what's happening between negative infinity to 0 and 0 to 1 and then 1 to infinity? Well, between negative infinity to 0, when I put a number in to my second derivative, right, I get a positive output, which means we're concave up. If I put in a value between 0 and 1 into my second derivative, let's just say a 1/2, I'm going to get a positive times a negative, which is a negative. That's concave down. And then if I put maybe a positive 10 in, I'm going to get a positive times a positive, which is a positive, which is concave again up. So our concavity, fun stuff happening here, concave upward from negative infinity to 0 and then 1 to infinity, and then concave downward from 0 to 1. And I think we got almost everything. We just have to do our points of inflection. Our points of inflection, 0 something and 1 something. So now I have to find f of 0. F of 0, we go back to our original function, and we put 0 in and we get a 1 out. And then I have to find f of 1. We put a 1 in, and I get 1 minus 2 is negative 1, plus 1 is 0. So 0, 1, and 1, 0. So my points of inflection are 0, 1, and 1, 0. And now I believe in this problem right here, we single-handedly found extrema using the second derivative test, hot dog. We found the concavity of this graph and the points of inflection. So there's lots that we could do here without a calculator. We could graph these points of inflection. We could sketch our concave upward and our concave downwards. We could locate the relative minimum. It's fantastic what's going on here. It's truly fantastic. So much so, I'm just going to show you, because you got to get this picture in your head. Okay. Now, I'm going to move this over because things are happening at 0 and 1, right? Things are happening at 0, 1, and 1, 0. 0, 1, 1, 0. Now, these are important parts of the graph because our concavity is changing here. We also have a relative min. Where's that relative min occurring? At 1.5, comma, negative 11/16. So somewhere right here, we've got a relative negative 11/16 is going to be a little bit more than 1/2. So we've got this happening. So what's happening right here? We've got, oh, let me take this off. Look at this. This is truly amazing, not gonna lie. Okay, so there's negative 11/16. So what's happening here is our concavity changed right here at 1, 0, and it's concave what? When x is equal to 1 to infinity, look at this. Look at this. Right there, we've got concave up. So what's happening, I don't know what the x-intercept is, but I could find the x-intercept if I wanted to. That section is concave up. We've got our relative minimum. We've got our point of inflection. So what's happening this way? We've got concave down. Look at that. Concave down, right? This is fantastic. I don't know if you see how fantastic this is, but oops. Yeah, let's use a third color. Look at this. Concave down right here. And that's what I just drew right here, concave down, right? And then we had our point of inflection, concave up. And then what's happening? Well, in this green section right here, from negative infinity to 0, we're concave up again. So, look, this is what's happening. That's what's happening. That's our graph. That's the graph of this. I mean, if that's not exciting, honestly, if that's not exciting that we just sketched that graph and put that in your calculator, that's a refrigerator picture right there, a refrigerator picture. Take a snapshot of it, send it to Costco, get a big picture printed, put it on your refrigerator. Better yet, take a picture of your own, because I bet it's just as fantastic.